Hello, everyone. Welcome to the final part of Data Science Conference Europe 2020. We will begin this part of the program with a keynote presentation from Dr. Bob Sutter, which is titled Overview of Quantum Computing Ecosystems. Dr. Bob Sutter is Vice President for IBM Q Strategy and Ecosystem at IBM Research. He's responsible for driving strategy, ecosystem, and awareness for the IBM Q Quantum Computing Program. In this role, he works across IBM to bring together essential functions to rapidly extend the footprint of IBM Q as the industry-leading quantum computing hardware-software platform. While based at IBM Research, headquartered in Yorktown Heights, New York, he travels to meet with clients, speak at conferences and universities, and he's a primary spokesman for IBM Q to the media as well as industry analysts. Sutter has been with IBM for 35 years, more than 20 of which at IBM Research. Dr. Sutter, thank you so much for being here with us.
Thank you. Pleased to join you. All right, let me bring this up full screen. Just one second. All right. May I ask, can you see this okay?
Yes, it seems to be fine.
Okay, very good. All right, thank you. So today I'm going to be talking about quantum computing. And as the title says, we're talking about the ecosystem. Now, what exactly is the ecosystem? Well, it's really the people who are creating quantum computers, the hardware, the software, the systems, putting them on the cloud. It's the developers, the coders. And I think, as we all know, when we talk about developers, we can talk about people who write code that's down very close to the hardware, all the way up to people who really want to have just some very easy to use facilities where they can actually build applications. Now, one thing I want to say right up front is that nobody on the planet has quantum computers that can do more than we can do with classical computers, right? It's going to be several more years before we go past that. And I'll talk about that notion. So when we talk about use cases, we are not talking about use cases tomorrow. We're talking about use cases that we are working toward over the next several years. So let's start with this. So we're a small planet with big problems to solve. Well, what this means is that we have always been reliant, at least let's say for the last 50 years or so, on the increasing amount of computing power. And it's shown itself in different ways, from mainframes in the 60s. In the 90s, we had the web and servers. And now, of course, today we have mobile phones. And really, for most of us, our mobile phones would have been considered a supercomputer perhaps 30 years ago, right? But as we come across these problems, we want to do more and more and more, right? Every time we get an increase in computing power, we want even more so we can solve bigger problems or solve different problems. So it's important to ask, can we keep going like this, right? Is our ingenuity, is our innovation such that we can continue to increase the performance, the capabilities of our computing systems to match our need for these? Well, classical computing, it goes back to the 1940s, really. And it's based on the notions of zeros and ones, which are bits. And we put bits together and get bytes. And you put a million of those together and you get a megabyte, and a billion, you get a gigabyte. And whether we're talking about storage or memory or processing power, it all really, somewhat surprisingly, comes down to a lot of zeros and ones. This is the system we designed. It works very well. There are all sorts of computer science theorems that say, well, we can do any sort of computation with zeros and ones. What they don't always tell you, though, is that, yeah, we could do that computation. It would just take 150 million years, or it would take more memory than we can possibly scale. So we're beginning to hit this boundary. While certainly classical computers, supercomputers, tremendous amount of value, we're certainly identifying certain types of problems that we're just not going to be able to tackle in a reasonable way with classical computers. So the future isn't just ones and zeros, which means that there's got to be something else. We've got to go on beyond just plain classical bits here. And of course, this is what quantum computing is all about, and this notion of qubits or quantum bits. Quantum computing is based on the laws of quantum mechanics. Now, you do not have to take several years of physics and learn all about quantum mechanics to do quantum computing, just in the same way as that if you're going to write an app for your smartphone, you don't have to learn about transistors and the physics behind them. All right. Now, we're earlier in the stage, you perhaps have to know more technology than you do today with classical. But the main point here is that nature itself, in the very small, so here we're talking electrons, photons, atoms, uses this model of quantum mechanics. At least that's what we believe right now. And it does it in such a way that there's a tremendous amount of information, a tremendous amount of processing power. So can we tap essentially nature as a big computer, or at least that model, and apply it to our problems? So the diagram in the middle uh, gives you an idea that, well, certainly there's an overlap between what we can do with quantum and classical. Quantum computers will not just completely replace classical computers. There is no need. Classical computers do many things extremely well. We will keep using them. So, in fact, when I talk about quantum computing, I speak about quantum computers plus classical systems. So, a quantum computing system are quantum computers plus classical systems, right? It's not one or the other. It's how do they work together? And exactly the ways in which they will work together is what we have started on and what we will be working on through the next few years, certainly the next few decades, and for all I know, the next few centuries. I won't be around, so I don't really know. And there are different types of applications. And as you get more deeply into this, you realize it's not any type of hard problem you apply quantum computing to. It's just certain classes of problems to which you want to apply it. And as you learn more about that, as you are thinking about applications, you begin to recognize, you at least say, okay, this thing we're trying to do over here, this is probably something we should investigate as a use for quantum computers. But this other thing over here, well, no, it really isn't going to give us an improvement. So we're going to do as well as we can with classical computers. So these are a few examples, and these are some examples which really are related to chemistry. And the reason why is, well, it's likely that the first breakthrough applications will be related to chemistry. Because as I said, quantum computing is built on quantum mechanics, which is nature, physical systems. So using quantum computing to represent and do computations for physical systems based on quantum mechanics makes a lot of sense. So for agriculture, right, creating better fertilizers, being much more efficient, using much less energy than we do today, using much less natural gas than we use today, to do it in a more sustainable way. In the same way, in the oil, petroleum, but really more generally the energy industry, can we create new and better catalysts for all these chemical reactions, which are in all the processes we use? Can they be more efficient, right? Again, once again, to be more sustainable, use less energy. Big areas, electric batteries, new vehicles, right? We will need them to be more efficient. We need our batteries to last longer, to put out more output. So whether we're talking about vehicles, cars and things, and eventually even aircraft, right? Can we get to that point? You want to be able to model this exactly. See, this is the point. You don't just want to do approximate calculations. We can do that now. Ultimately, we want to be able to say, can we fully, with great fidelity, right, represent molecules in a computer so that we can simulate the reactions inside a computer, inside a quantum computer, rather than the expensive, laborious, and sometimes dangerous ways of doing it in a laboratory. And of course, what people always want to know are things like antibiotics. And this year with COVID, I want to say right up front, there is nothing that quantum computers today can do for COVID. There was some marketing hype from some people early in the year, but We cannot do anything, unfortunately. And it's simply because these types of molecules are much larger than we can work with today with quantum computers. It will be several years, maybe even into the next decade, before we'll be able to handle molecules of that size. So these are the three main areas. And for this audience, I decided I wanted to get a little bit more technical. So the first area, as I talked about just now with chemistry, quantum simulations. And by simulation, I mean, as I said, can we consider a molecule and represent it exactly inside a computer? Because if we could do that, right, it would have a lot of bearing on how we do physics, how we do engineering, how we do chemistry, and especially materials discovery. Materials discovery is likely to be one of the first really important commercial applications of quantum computing. Second, linear systems, and this is kind of general. Mathematically, we're talking about linear algebra, and the reason is really the math behind quantum computing. It's a lot of linear algebra. So we start thinking, well, where is linear algebra used a lot? Well, it's used in AI. It's used in machine learning quite a bit. It's used in areas like computational fluid dynamics, many different areas as well, differential equations and so forth. So this is a question of saying, can we do the math better and faster for the sorts of applications we have today, which are already doing similar math? Now, in the case of AI, it also means saying, well, quantum computing is really a completely different programming model. As I said, it's not simple bits. It's much different from that. It has some very peculiar properties, which are wonderful as well as initially very confusing until you get used to them. So is there something about the programming model, again, using the mathematical basis here, that will allow us to do operations like classification better, right? Can we actually do training much faster? Can we get insights through new methods that take advantage of, for example, quantum entanglement, which I will not define today, but that has no counterpart in classical computing, right? So can we use that whole new type of facility to somehow come up with new algorithms to do things more efficiently in areas like machine learning? And then quantum walks. And here we're really talking about combination of things, combinatorial types of problems, um, optimization types of problems that involve probabilities, stochastic optimization, things like this. And a lot of that goes back to simply because quantum computing, like quantum mechanics, is probabilistic. It is not deterministic. One thing doesn't necessarily always follow one after the other. This is what gave Einstein so much pause. He had a lot of problems with quantum mechanics. So the part of his quote, which was something like, God does not play dice with the universe, this was his saying, look, he didn't like the idea of probability being part of the model for the universe. And therefore, he would have said the same for quantum computing today. So just to give you an example, here is the caffeine molecule. And it's not a very big molecule. I've had 2 cups of coffee this morning, maybe 1.5. I have ingested trillions, quadrillions, gazillions, I don't know, caffeine molecules. And I would like to say, well, let's look at this molecule here. And I want to fully embed all the information about this molecule inside a computer. How much information does that represent? Well, if I were just drawing the picture, it wouldn't represent very much information at all. But now if I start to think more from a quantum sense, and I think about the electrons, and I think about the chemistry, and how these are all related, things get much more complicated. And so I could do this using 160 quantum bits, 160 qubits. Now today, for IBM, our largest computer is 65 qubits. I'll show you our roadmap in a few minutes. And we plan to get well above 100. And then there are also some deeper questions about error correction and so forth. But the point being is that we will need a pretty big quantum computer that goes beyond, um, uh, well, to be explicit, we need 160 logical qubits, which represents thousands and thousands and thousands of the types of physical qubits we have in our machines today. But nevertheless, this is in sight, right? Now, if we think about modeling it, though, classically, and again, we think of the electronic structure of just that molecule, and how many bits, how many zeros and ones would it take to represent that? Well, we'd need about 10 to the 48th. And that number, incidentally, is 2 to the 160th. Now, scientists estimate that the number of atoms in the planet Earth is between 10 to the 49th and 10 to the 50th. So in the worst case, just to think about large numbers, we would need the number of zeros and ones comparable to perhaps 10% of the atoms in the planet. That's not going to happen. I don't care who your commercial storage provider is, no one's going to have classical storage that much. So this is an intractable problem today. It's an impossible problem effectively for classical computing, but should become possible over the next, let's say, a couple decades, right, for quantum computers. Okay. So this point where we start doing better than classical computers is called quantum advantage. And so it's the point where universal quantum computers. Now, I've mentioned this word universal because this is really important. I must warn you that people use this word quantum in bad ways, sometimes, shall we say, marketing ways. So just as we think of your laptop as your smartphone, as a supercomputer, as a universal classical computer, that is, it's Turing complete, right? We also must think of universal quantum computers. That is, they can actually execute anything within the programming model. There are systems that are out there that use the word quantum that are not quantum in the slightest. And there are systems out there that label themselves as quantum, and they are not universal quantum computers. However, almost everybody, not all, but almost everybody that is doing quantum computing systems today is working on universal quantum computers. So this includes us, of course, and people like Google and a few others. Okay, so the point where universal quantum computers plus classical systems can solve currently intractable problems or perform significantly better than classical systems alone. And moreover, I don't really, well, I don't really care. It's nice to consider something that happens in the back of a laboratory, but this has to be relevant to real world problems, right? Um, the things we do in the laboratory will advance toward and helping these use cases for society or industry. But quantum advantage is really where it starts becoming, quantum computers start becoming useful and valuable for people as opposed to just scientists. So remember this term, quantum advantage. That is what we are after here. So now I'm going to talk about the IBM Quantum Program for a couple of reasons. One, hey, look, I work for IBM. I'm in the IBM Quantum Program. But the second reason is, to be really honest with you, and you can look up the numbers, we are by far the most advanced quantum system in terms of hardware, quality of hardware, software, number of users. So I'm in the very lucky position of, yes, I work for IBM, but yes, we have the most advanced systems that are out there. And so therefore, what I want to tell you is about what is the state of the art, or what is the best that is out there. It happens to coincide with what IBM has. I apologize if you think that's marketing, but if you do your independent research, you'll see the same. All right. Sometimes people like to say, well, we're very early with quantum computing. Hardly anybody is doing anything. Well, yes, we're early. We have to reach quantum advantage, but we've had over 275,000 users. The things that people run on quantum computers are called circuits. So when you send a little bit of code over to a quantum computer, that is called a circuit. We've had 550 billion hardware quantum circuits run on our machines. I checked this number last night. Right? On a typical day, People run over 1 billion circuits on real hardware. People like to talk about software simulators and things like this. This is real hardware. The future is real hardware, not classical simulation of quantum computers. And we have many quantum computing systems on the cloud. I say about 20. The reason is because we're always putting in new and better ones. Sometimes a few older ones come off. So right now the number is about 20, and that will inch up over time. Whatever number I gave you today, in 2 weeks, it might be slightly different. So far, we have, as I said, we've been out there on the cloud for 4.5 years. The two best systems in slightly different ways are the 27-qubit Falcon class we introduced last year and the 65-qubit Hummingbird class. They're different. They're best in class in different ways. The 27-qubit Falcon has the best performance, but the 65-qubit Hummingbird is the largest. So we're tackling different problems. And so over time, you have to look at both those dimensions if you're thinking of a graph. So are the systems becoming big enough to solve large problems? But is the performance, is the quality of the computation good enough to also solve those problems? So a lot of those ideas, plus other things we've been working on, will converge. Next year, we plan to release a 127-qubit machine, codenamed Eagle. Now, this is going to be very important. Breaking that 100-qubit boundary is going to be a technological milestone, as well as, I would say, an industry psychological milestone. The following year, we're going to go above 400 qubits. And then in 2023, we'll break another important boundary, which is 1,000 qubits. And then in different ways, and we've spoken quite a bit about this. If you do a web search on the IBM Quantum Hardware Roadmap, we have a lot of information, particularly about this latter part. And we're going to need to get well above 1,000, and new technologies will have to come along. As we progress from left to right here, you will be seeing increasing miniaturization. You'll be seeing moving from quantum devices. What I show here on the bottom left, that's a Hummingbird chip. Actually, it's two parts of the device there, the top and the bottom. We will be going from quantum chips to quantum motherboards to multiple quantum motherboards in very large dilution refrigerators, which is what we have an artist rendition on the right-hand side we're building. And that's how we will get beyond 1 million qubits. Now, it is not simply a question of making more qubits. One of the most important things is qubits need to work together, right? If you have 250 qubit machines, you put them together, that doesn't give you a 100 qubit machine. It still gives you 250s, right? And so the engineering of making all of this work together while decreasing the noise, decreasing the error rates, and all these things is very important. So this is how we're going to do it. Now, it's also very important, and a little bit of a footnote here is this is the scalability story for the technology we are using, the superconducting technology we are using. Everybody who makes quantum devices is going to have a scalability problem. So when you look and you say, oh, somebody has 2 qubits, or they have 9 qubits, or they have 15 qubits, that's nice. It might be fascinating technology, and a lot of it's really interesting. I mean, there's terrific science that's going on around the world. But the question you must ask is, how are you going to scale above 100? How are you going to scale above 1,000? And the degree to which they kind of wave their hands and talk about a miracle happening somewhere will lead you to believe that they know how to do it, right? They're confident, or, well, they hope they come up with something clever, or there's a lot more science than engineering. There are a lot of people who are parked in the lower double digits and don't really know how they're going to get really big. Now, they've announced they're going to get big, but they don't actually know how to do it. What I'm telling you with this slide is we know how to do it, and you will see this year after year starting next year. So getting back to the ecosystem idea, there are lots of people involved with this. You have to give people access to the technology, especially early on. You have to look at what are the skills and training, right? You have to look at the applications to industry and the economy. This is why so many governments are interested. Yes, they're interested in security. Yeah, I get that. but they're interested in how will quantum computing create better businesses, right? How will it drive the economy? And then there's just straight up research, the people who are working on the very basic technology, whether it's in industrial labs like IBM Research or in universities around the world. Our program to bring people together, and all these people are working toward quantum advantage, is called the IBM Q Network. If you look through these names, you'll see, well, particularly on the right-hand side, many universities, but you will see other names like Boeing, like Daimler, like JP Morgan Chase, banking. There are insurance companies. There are energy companies. These are all people who are somehow invested in working with us, either in our free-to-use system. So of those 20 systems I mentioned, about half of those are completely free. You can go to the IBM Quantum Experience, do a web search for it, log in, and you can be using actual quantum computers in 5 minutes at no charge whatsoever. You can get up and running. You can have access to Quizkit, which is the open source programming kit, no charge, open source. Many of these people, though, are working on state-of-the-art programs. So not all these people, not all these organizations are doing the same thing, right? They may be doing different types of research, and you would expect people in very different industries to be working on different problems. Financial services, we have chemistry, we have all these sorts of things. A lot of startups are in here as well, right? Because we want to give access to quantum computers to people who are thinking these great ideas about how to take advantage of it and use it. So this is our community. This is our ecosystem of organizations around the world, in addition to those 275,000 people, or maybe including them, right, that have access to real quantum computers today, even though quantum advantage is a little way off. These people aren't just playing, they're writing papers, right? To date, we've had over 400 papers written using the real quantum computers that we have made available on the cloud. So by our making these machines available, it is driving research around the world related to quantum computing. So everything we're doing, right? The ecosystem is about accelerating toward quantum advantage. That's what it boils down to. And on the many different levels, right? Well, okay, I showed you a list of a few companies there. If this does continue, and we certainly think it will, and people start using quantum computers more and more, they're going to need employees. And in fact, when I speak with people, whether it's on LinkedIn, and by the way, please, if you'd like to connect with me, please do. They want to know what classes should they take, what training should they get, who is hiring, what do they need to know? How do we build a quantum workforce so that all these organizations and people who will be adopting it later, right, have people to hire, or people who already work there who have brought up their skills with quantum, maybe even quantum and AI, quantum and data science, right? And this is why we drive the open access. This is what I said about the roughly 10 computers on the cloud that are no charge, open source. You can use it, you can extend it, and education. All right. Education, education. So I pointed out before, we will have over 1,000 qubits in 2023. That's when people can really start, we think, approaching quantum advantage. It may take a little while, but we think they're going to get there. So, gee, you start thinking middle of the decade. Who will be in the workforce in the middle of the decade? Well, people who are there now, but people who are in colleges and universities. So the more we can do to train them now, the more skilled people we will have to use and extend this technology by the middle of the 2020s. So quantum experience, this is where you can get online. You can use real quantum computers, and you can either do the drag and drop environment, right? So you can build, if you buy a book, I happen to have a book about quantum computing. There are quantum circuits in there. You can build those using a drag and drop environment. You can run them. Or if you want to do some coding, we have Jupyter notebooks We have many examples, we have many tutorials, and you can do all your work in Jupyter Notebooks with Quantum and Quizkit as well. Quizkit itself is moving along. It's been available since 2017. It's now actually version 23. I need to update this slide here. We've had over 500,000 downloads of Quizkit through the years, through all the different versions. Now, when you use it online in your browser, you don't download it. Yet these numbers of people who are downloading it, typically to their laptops to use, keep increasing. That number at the beginning of the year was 400,000, maybe a little bit less. So this is a very, very active application or software development kit for Quantum. It works on some other qubit technologies other than ours, and we invite everyone to use it for whatever hardware they are using. From a software development perspective, we want you to think of it like a Linux. That is, you can optimize the back end to work with your hardware, but you can code in general. There are other software development kits. If you look at GitHub, look at the stars, right? Look at the forks, however way you want to get a sense. Quizkit is by far the industry leaders. There's Quizkit, the numbers are way at the top. The lead over the other ones is increasing, and all the other ones are bunched together at the bottom. So, extrapolating from that, all goes well. We continue to train people. This is going to be the leading one. This is what is taught in so many classes now. Over 100 different courses around the world use Quizkit. Now, we had an event this last summer. We called it the Quizkit Summer School. Last December, we had a summer school in South Africa because it was summer in December in South Africa. We had 200 people show up. So this was a 2-week event. Obviously, with COVID, we could not do it in person this year. So we said, hey, let's do it online. All right. We got more than 200. We thought we'd get 200. We had over 4,000 registrations, and at a given lecture, if you look at how many people actually showed up, there were close to 4,000 people who spent hours to do this. If you look at Quizkit Summer School, these lectures are all available for free. You can see them on YouTube. You can find them from the Quizkit website, which is simply quizkit.org, or you can go through Coursera. And on the right-hand side, the upper right side, you can see there were about a quarter of them were undergraduate. There were master's and PhD students, but there were other people from industry and even high school students. So what I want to tell you is that this ecosystem involves teenagers all the way up through people established in industry and often established in other fields. We had another offering with a coding school to have a 2-semester online class for 5,000 students. We filled that within days, 10,000 applicants. We have special programs for educators and for researchers, and they can get priority access to certain systems at certain times. That is, they don't have to wait in the general queue. They can get in there, they can do the work, they can teach, they can do whatever they'd like to do. So I hope this gives you an idea of where we are related to the development of quantum, what it's going to look like over the next few years, maybe what some of the issues are that people will face over the next few years. But the single goal is quantum advantage, right? And we are doing this with many different people across the ecosystem. I very much invite you to join us. Thinking of data science, there is work being done with quantum and machine learning. I want to tell you, though, it's very early. Quantum computers are not big data machines. So sometimes I joke that if you talk about quantum and AI on the cloud, you win because that's 3 buzzwords all at the same time. Quantum computing is available on the cloud, right? I've shown you all the people. They've run over 500 billion circuits, right? But an interesting area for you, for this audience to get involved with is how might it help machine learning? Now, when it will help machine learning, right? What is research? What's academic research being applicable? That's much more up in the air. And how will it do it? But it is an area of active research, but it will not help you tomorrow. So you can jump on in. There's a lot of papers. There's a lot you can use. There's a lot you can experiment with. But get started. So with that, thank you very much. Thank you for the opportunity to talk to you today.